Exercise 3, we want to do a hypothesis test. In particular, we have a telephone company, and according to their records, the average length of all calls is 12.44, and they want to test this claim that they want to test whether the average length of a call is 12.44 minutes or not. So let's set up our hypotheses. So we have our null hypothesis and our alternative hypothesis. We want to test if the mean is different from 12.44 minutes. So if we want to show that the mean is different from 12.44, that'll be our alternative. And then our null hypothesis is just the opposite. One thing you'll note here, this is called a two-tailed hypothesis test. And it's two-tailed because of the alternative hypothesis. In general, we determine what kind of hypothesis test it is, left-tailed, right-tailed, or two-tailed, based on the alternative. The alternative here, we look at the sign in the alternative hypothesis. The sign here is a does not equal sign, so it's two-tailed. If, on the other hand, our alternative was that the average was less than 12.44, this would be a left-tailed test. And a rule of thumb for remembering that is that the sign in the alternative hypothesis is pointing left. It's a less than sign, so it's a left-tailed test. Similarly, if the alternative were that the mean were greater than 12.44, this is pointing right, so this is a right-tailed test. So that's just a review of how we determine what kind of test it is, what kind of tailed test we have. All right, we're also given that our sample size is 150 and that the sample mean, so the mean of these 150 sampled calls, is 13.71, and we're given the population standard deviation, which is 2.65 minutes. And last, we have a 2% significance level. So, step 2, we need to write down the appropriate test statistic and the rejection region of our test. So let's first figure out what the appropriate test statistic is. Well, we're given the population standard deviation, so in other words, sigma, the population standard deviation is known. Second of all, we know that our sample size is 150, so we have a large sample. And last, we'll assume the sample is random. Since we're given the population standard deviation, since we know it, and because we have a large random sample, we can use the normal distribution. In other words, we can say that our sample mean is approximately normally distributed with standard deviation equal to the population standard deviation divided by the square root of the sample size by the central limit theorem. So we can use the normal distribution. So our test statistic is the z-score. So it's our sample mean minus our population mean divided by its standard deviation. So we have our test statistic. Next, we find the rejection region of our test. The rejection region is determined by what kind of tailed test we have. Remember, we said that since our alternative has a does not equal sign, we know that we have a two-tailed test. So I'll draw my normal distribution with two tails. Next, we'll use our significance level. We know that our significance level is 2%. So that means that the area in both the tails together is 2%. So the area in each tail is half of 2%, or 1%. So now I want to find the z-scores corresponding to these areas to the left and right. Because what I'm going to do in my hypothesis test is, well, my null hypothesis is that the population mean is equal to 12.44. I'm going to reject this hypothesis if my sample mean is a lot bigger than 12.44 or a lot less than 12.44. If it's a lot bigger than 12.44, it's going to be in our right tail. If it's a lot smaller than 12.44, that's represented by our left tail. So we're going to reject when our test statistic is in this tail or this tail. So let's figure out what these z-scores are. So I want to find the z-score with an area to the left of 0.01 or an area to the right of 0.01. I can look that up in my z-table and I can find that this z-score is 2.33. And this one is negative 2.33. So in other words, we reject our null if our test statistic that we calculate here I'll differentiate these two by writing a subscript for these ones. So I'll reject our null hypothesis if our test statistic is less than negative 2.33 or if our test statistic that we calculate is greater than positive 2.33. These values here, 2.3 and negative 2.33, are what we call our critical values. They're the boundaries of our rejection regions. So now let's calculate our test statistic. So it's equal to our sample mean minus the population mean divided by sigma over the square root of n. We're given our sample mean, which is 12.44. Oops, that's not right. Our sample mean was 13.71. And our population standard deviation was 2.65. And our sample size was 150. Now, what do I plug in for mu here? I plug in the value from our null hypothesis. Because I want to see how different our sample mean is from the hypothesis value of 12.44. So let's plug this into my calculator. 13.71 minus 12.44 divided by this stuff. You should get 5.87. So we know our rejection region. We know our test statistic now. Let's make our decision. We said we would reject our null hypothesis if our test statistic was greater than positive 2.33 or less than negative 2.33. Well, I can see that 5.87 is a lot bigger than 2.33. So I will reject the null hypothesis because the test statistic is greater than 2.33. And therefore, we conclude that the population mean, the mean of all phone calls, the length of all phone calls, is not 12.44 minutes. So what did we just do? We made our hypotheses based on the claim we wanted to test. We wanted to test whether the phone call length, the average length of all phone calls was 12.44 minutes or not. So we set up our null hypotheses. Next, we determined that since the population mean was known and because we have a large random sample, our test statistic will follow a normal distribution. And then, since we know that we have a two-tailed hypothesis test based on our alternative hypothesis, we know that we have two rejection regions, one in the right tail and one in the left tail. Our significance level, alpha, was 2%. So therefore, I know that the area in each tail is half of 2%. Knowing that the area in each tail was 1%, I found my critical values, the boundaries of my rejection regions. So then, I know that my rejection region is less than negative 2.33, or greater than 2.33. These two tails. Then I calculated my test statistic. I got 5.87, which is definitely bigger than 2.33. So I rejected my null hypothesis and concluded the opposite, that the average length of all calls is not 12.44 minutes. That's the critical value approach. Another approach we have to a hypothesis test is called the p-value approach. So in this case, we calculated our test statistic, which is 5.87. Remember that the p-value is the probability of seeing a test statistic as or more extreme than our observed value, 5.87, assuming that the null hypothesis is true. And if our p-value is less than our significance level, which in this case was given to us as 2%, we reject the null hypothesis. In other words, if the probability of seeing a test statistic as or more extreme than ours is really small compared to 2%, then we reject the null hypothesis, because the probability of seeing such a test statistic, assuming the null hypothesis is true, is really small. So probably not possible. So let's calculate this probability and compare it to 2%. So because we have a two-tailed test, when we're talking about as or more extreme, that's in both directions. So extreme as in greater than 5.87, so extreme in the positive direction, or extreme in the negative direction, less than negative 5.87. So what's the probability that a z-score is greater than 5.87? Well, if I look that up on my normal table, this z-score is so big that it's not even on the table. The area to the right of a really big z-score is near 0. Similarly, the area to the left of a really negative z-score, a really small z-score, is also near 0. Hence, our p-value is approximately 0. So now let's make our decision. Is our p-value of 0 less than 2%? It sure is. So since p-value is less than 2%, we should reject our null hypothesis and conclude that the population mean is not 12.44 minutes. Regardless of which approach we choose, the critical value approach that we did up here, or the p-value approach, we should always get the same conclusion in both. If you didn't, if you got a different conclusion, let's say you rejected the null hypothesis in the critical value approach, but accepted it here, that's a good sign that you did something incorrect. So these two approaches will always give you the same results. All right, so we've determined that we should reject our null hypothesis. The last question we have to answer is, what kind of error could we have made here? In general, we're always talking about either type 1 or type 2 error. In fact, here, we could have made type 1 error. And that's the error in which we reject the null hypothesis, when in fact the null hypothesis is actually true. As a side note, type 1 error has everything to do with the significance level here. What does this 2% mean? How did we choose 2%? This significance level here, 2%, or alpha as we call it, is precisely the probability of making a type 1 error. So in general, that's why we always pick a very small number, like 2% or 5% for a significance level.